Good morning, everybody. I hope you guys are doing well. It's a lovely day outside, and hopefully it is when you're watching this. So I'll keep it short and sweet so you guys can get outside and get your stuff done and enjoy the weather. So acids and bases is what we're going to start with chapter 16, and you probably have had a lot of prior experience with acids and bases. So this will go fairly quickly. Acids and bases are something that, our bodies are fine-tuned machines, and pH and acidity of different solutions in our body that we'll talk about is very important. So the first thing is we obviously need energy and we need food to eat. Most of the food that you eat is acidic and does have a taste sour. You probably are thinking of lemons and oranges or maybe some of that sour candy that you might be enjoying. However, even milk is slightly acidic. Then on the opposite side of the pH scale would be things that are called bases, and those are bitter in taste, and this would not be anyone in here because I know you guys are a bunch of angels, but on the outside there, maybe you had to have a little bit of soap in your mouth and you know that tastes bitter. Those of you that have never had that experience, congratulations. Maybe you have tasted real chocolate or coffee grounds or real strong coffee. That's bitter. But most things that we have are on the acidic side. So I mentioned the word pH. We know that the pH for acids is going to be less than 7, and we will learn more about what pH actually means in the next unit or the next sections. For bases, the pH is going to be greater than 7. And then right in the middle, we have a pH is equal to 7, and that is going to be all of our neutral substances. You may recall that the pH scale does go from 1 to 14 or 0 to 14. You can have substances that are less than 1, less than 0, and ones that are greater than 14, but they be the unusual ones. Acids always produce hydrogen ions. And bases are in our cleaning supplies. And they are very slippery to the touch. So hopefully you have used some soap today and you can attest to that. We'll add some more to this about indicators and what indicators change in the presence of an acid and a base. So we're just going to keep this simple right at the moment, and we will come back to this. Now, we're going to learn about some theories and how to classify acids and bases. And the first model that we're going to talk about is the Arrhenius model. The Arrhenius model said that acids produce hydrogen ions in an aqueous solution, and bases produce hydroxide ions in aqueous solutions. So the last chapter was all about solutions. Now we're going to take a look at acids being shown by hydrogen ion and bases shown by hydroxide ions. So here's the example. You guys know that hydrochloric acid is a very strong acid, and so what that means is that it dissociates or breaks apart 100%. And so it completely breaks down. So then I can go ahead and write hydrochloric acid. We know that it's going to be an aqueous solution, and when it breaks apart, it's going to break apart into its 2 ions. Now, the more hydrogen ions that are there, the lower the pH, the stronger the acid. And so those are some of the things that we will be studying. On the other end, he classified bases, and the same thing, if you have a strong acid, it fully dissociates. If you have a strong base, it does the same thing. So here I have NaOH, and again, that's going to be aqueous. That's going to break apart when you put it into water to sodium ions plus the hydroxide ions, which the number of the hydroxide ions is going to tell you how basic the substance is. Now here's the question. Arrhenius did not understand that there were other forms of bases. Do you think that all bases are going to have the hydroxide anion? And the answer is no. You guys probably used some toothpaste this morning, some baking soda, some shampoo. They all have bases in them, but none of them have hydroxide. They'd be very, if they had hydroxide, we'd have a lot of sores and our skin would start to crack and things like that because it's pretty strong. So there are other bases there, so we had to come up with another model. And this one's more general. So this is the one that we're going to stick with most of the time and talk about, is the Bronsted-Lowry model. And so he said that acids are going to be proton donors and bases are proton acceptors. Now, where does that word proton come from? Well, in the acid, if we know that we have hydrogen, atomic number 1, mass number 1. So that means that I have 1 proton, 1 electron, and 0 neutrons. All right, so if I have hydrogen with a +1 charge, you know that that is a loss of an electron. So all that's left is 1 proton. So that's where the term proton donor came from. So you're either donating a hydrogen or you're accepting a hydrogen. And here's the general reaction for involving water. So you can see HAH, all acids start with hydrogen. And then we have water and we get what's called the hydronium ion here. So that H3O is a hydronium ion and then the base. So the general form that you might see me doing a lot of the time is without water. So we can say that we have the acid breaking down into its 2 parts. Now we're going to try to label some of those parts in terms of how they react together in an equation. Okay, so if we take a look of these acids, we're going to have a partner. They're always going to have a partner. We like to have partners whenever we do things out and about. It's a lot more fun to share our life together with someone else. Well, the same thing happens here with acids and bases. They are called an acid conjugate base pair, and then we have a base conjugate acid pair. So what you have to think about is go back to the definition of the Bronsted-Lowry. It said that acids are proton donors. Bases are proton acceptors. So if I take a look at this, you can see here's my HCl. It's bracketed over here with the chlorine, and you can see that the hydrogen is not there anymore. So it became a proton donor. So this is going to be our acid. Then if I take a look at water, you can see how it's paired up, that it accepted that hydrogen. So here's its base. And then with the acid, that means over here is our conjugate base. And with the base, this is our conjugate acid. And remember, the word conjugate means to come together. So if I take a look at this, if this is very, very strong, which is, these are things that we need to remember, if I have a strong acid, its conjugate is going to be very weak. So it doesn't have a lot of properties on the basic end over here. However, if in this case water is pretty weak, then its acid, its conjugate acid, is going to be strong. So they flip-flop like that. So the biggest thing that we need to do is we need to be able to figure out what is what here. So the first thing that I would say is I would encourage you to bracket these things up so you can look at each half reaction one at a time. So I see nitrogen here, I see nitrogen over here, I see hydrogen and oxygen here, oxygen and hydrogen over here. So now if I take a look, I can see that this NH3 is becoming NH4. So it has accepted the hydrogen. So that means this is the base, and this over here is going to be the conjugate acid. Remember, they have to have partners. So this is accepting the hydrogen ion. Now, we don't always have to write that. We're just putting here in our notes so you can see that. And then if I take a look at my water, I can see that my water is donating a hydrogen ion. And so then this is going to be my acid, because acids are proton donors. And then the partner with the acid is going to be the conjugate base. And you should recognize that OH has basic properties, so that makes sense. All right, let's try one more, and then you guys can try some more on your homework here. So first step again, go ahead and bracket up the ones that are the half reactions together. So hydrogen and chlorine, here's my chlorine. Here I have hydrogen and oxygen again. So go ahead and take a look. Here I have HCl. Now I have just Cl, so that is becoming a proton donor. So this is going to be my acid, and this is going to be my conjugate base. Then analyze the other one. I have H2O going to H3O, so that's a proton acceptor. So this is going to be my base, and this is going to be my conjugate acid. Okay, and we are going to take a look next week and learn that water, if we take a look, you can see in both of these reactions, hopefully you're thinking, water here is acting as an acid and water here is acting as a base. Can that happen? And yes, it can. And it has properties of both, and it's amphoteric. And amphoteric means that it can act in different, depending upon what the other thing is mixed with, whether it's going to donate or accept. So we'll study that in the next section. All right, so that's it for today. I hope you're having a wonderful day, and I will see you soon.